Sorry, it was a problem on my side. Sorry for that. Hi. Hello, Graham. Hello, everybody. Sure.
QB50 and a whole load of other good stuff. So anyway, let's make the introduction very short and ask you to go ahead. We've got the first slide up. Give me a shout when you want the next slide. We've lost the audio. Cry. We've lost the audio again, Jan. Can't hear a thing. Bright ideas from the floor.
Do you have, does it work on the speakers?
Go ahead, Jan. Yeah.
Where's the speaker?
Yeah, we can, yeah. Just, but it's some audio issue here we have. Keep talking, please. Just keep talking.
Okay. I was just saying, thank you
For giving me the opportunity to talk at this
guys, because you couldn't come. Yet that event is very important for me, and I want to make this acknowledgement right in the beginning. The support of the community of you who are there in the audience is absolutely enabling to this project that I want to talk about QB50. And it's not only the community, but in particular you, Graham. You have helped us a lot. Without you, we would be nowhere today. Can I assume that you can hear me? That you heard all what I just said?
Yes,
then I will go ahead. So we can go to the next slide. QB50, what is it? It's like in 2010 we have invited basically the entire world to join a common project here that with different objectives. It was about education, that's why we invited universities particularly to join, and it was also to do science in the atmosphere. We invited universities to provide us a satellite to send the satellites, but embark more sensors to do that science and to carry out a common project. We also do some technology demonstration I will talk about a bit later. The project as such consists of a consortium, among them is Surrey University, for example, and a community that is all those who have a satellite, and then there's the radio amateurs, the public, and so on. The VKI Projects, where I am now at the moment here in my office, we are leading this project. That's called in FP7 terms, the coordinator or prime contractor in ESA terms. We, together with this consortium, we support these universities when they're building their satellites. For example, with guidance, we'll give them also the sensor. The university have built a attitude control system, of which we'll provide some of them to these Cubesat teams. And we'll provide them with experience, for example, from the Precursor satellites, and you have heard already in a previous presentation about these Precursor satellites, which are our test satellites, to see what is working, what is not working. So QB50 is a space mission from end to end to the power of 3, how I call it. We're doing all the segments, ground segment, space segment. We do the science also. We do all the disciplines that are related to it. We're doing the science, the engineering. We're doing the managerial work. We do the legal work also. That can be difficult for engineers. And QB50, last but not least, is a project that encompasses all the phases from feasibility to operations. It's all in once, and because it's so compact, this project it has quite some challenges. We go to the next slide. Legal work also that can be difficult for engineers. And QB50, last but not least, is a project that encompasses all the phases from feasibility to operations. It's all in once, and because it's so compact, this project it has quite some challenges. We go to the next slide. Legal work also that can be difficult for engineers. And QB50, last but not least, is a project that encompasses all the phases from feasibility to operations. It's all in once, and because it's so compact, this project it has quite some challenges. We go to the next slide. Legal work also that can be difficult for engineers. And QB50, last but not least, is a project that
I have no idea what is happening now.
feasibility to operations. It's all in once, and because it's so compact, this project it has quite some challenges. We go to the next slide. Legal work also that can be difficult for engineers. And QB50, last but not least, is a project that
I have no idea what is happening now.
feasibility to operations. It's all in once, and because it's so compact, this project it has quite some challenges. We go to the next slide. Legal work also that can be difficult for engineers.
Stop it.
next slide, which shows the 3 sensors that we're using. And these are in situ sensors. Means what we're trying to do is we're measure not from a remote location, but right from within the thermosphere, the composition of it. And to that end, we have asked the University of Dresden in Germany to build feedback sensors for us, as shown on the very left side. They're measuring the atomic and molecular oxygen, and we have 19 of it. We have the INMS, the ion and neutron mass spectrometer. That's a development of University of College of London, the Institute MSSL. Say highly sophisticated instrument. Tested. Part of it was tested on the Tech Demosat, which samples oxygen, molecular and atomic, the nitric oxide, nitrogen, and the ions of all these species too. And we'll have a line mirror probe, is shown on the right picture, that measures the electron density, provided by the University of Oslo. We'll go to the next slide. So the in order for the science, for the measurement, we'll do also a modeling here of the thermosphere. We use a code that is provided by the University of Michigan. It's called GITM, a Global Ionosphere Thermosphere Model. If you are into fluid dynamics, you would find it very interesting. It's a Navier-Stokes code, so it really solves the physics behind behind that flow, behind that gas in the thermosphere. It's very typical, like a flow solver. It creates a grid on which the flow equations are being solved. It's 3-dimensional, so it's a simulation of the entire thermosphere in spherical coordinates, and it takes into account all the important input from, for example, and in particular, the radiation from the sun. And then as an output, it has the composition of the thermosphere, and you can derive then, for example, also the total density. If you go to the next slide, you see a sample of that of such a modeling. What we see here is the total density, neutral density, which is very high on the red spots and is lower at the blue spots. Yeah, and it's quite natural that the density is higher on the day side and is lower at the shadow side of in eclipse. If we do that, we go to the next slide. We'll be able to do predictions or computations already by now, and we compare that to available information. For example, there's the GEM satellites, a German satellite that measures, for example, the neutral density with an accelerometer. And that's the big disadvantage compared to QB50. GEM provides only one measurement in one location. So what we do at the moment is we simulate the thermosphere at different solar activities, high, medium, and low. We compare these measurements with we compare these simulations with the measurements of GEM. Sorry, and that's shown on the next slide. And this is very interesting and explains very well why this kind of research is so important. If you look at the figure on the top right side, we see a prediction carried out by us with this GIDM model versus a measurement of the GEM satellite. The GEM satellite measurements is the red and greenish curve. That's the total density in hours after a reference time. And we see that here the the CHEMP measurements and the GITEM modeling, they coincide quite well. But if you go to the left-hand side, on the top you see a comparison of the predictions versus the measurements for a low solar activity. We see that GITEM, the model, underpredicts significantly the measurements. And the opposite is the case for the high activity, where this state-of-the-art tool overpredicts the total density in the thermosphere. So we see here very clearly that the capabilities to predict the thermosphere, for example, the neutral density, which has obviously an enormous impact on your trajectory simulation, is just not good. And here this project QB50 can give a significant added value. We can carry out good science to improve that. And not only with one measurement, we will be able to do a multi-point measurement. No, means we will be able to measure at the same time backlit and sunlit locations. We'll go to the next slide. Practically, we're not only doing these computations for scientific purposes, but also for more practical purposes. We make an extrapolation of the solar activity for the time of our launch, which is then end of 2016. Measurements will be obtained somewhere at the beginning of 2017. So we will know that the solar activity will be rather low, but not at its lowest. So we'll be able to make predictions based on the solar activity of the last solar cycle. So we'll be able to pretty well say what density, for example, do we expect, and we can feed that into trajectory computations. So that's very theoretical, but also practical, what we do here when it comes to simulation. We go to the next slide. In order to participate in the science, we had to formulate some constraints to our participants in QB50, to these universities that we have invited and who have responded to us saying that they are interested to join. It's obvious that to join QB50, they had to build a Cubesat and of 2 or 3 unit size, and it's very common that the teams have proposed to build a 2-unit Cubesat. They had to accommodate our science unit, but our science units, they work only if we have a certain accuracy with respect to pointing towards the RAM direction, because these are in situ sensors, so they need to say be targeted towards the flight direction. And even there's a requirement even that's a bit more stringent when it comes to pointing knowledge. It's ±2 degrees. Since we could not have downlinked all this data with one ground station, we had to ask each team, and they gladly did so, we had to ask each team to have access to a radio amateur ground station. And of course, we need to ask the teams to downlink 2 megabit of data per day, and also to send us. Otherwise, we would not have access to the data. We could not carry out our science. So far for the science, we have a small number of other satellites. Among them is the VKI satellite itself that serves not these thermosphere science purpose, and that's shown on the next slide. We call them the in-orbit demonstration satellites. We have also invited the university to propose technology that may have a great potential to just test them in space. We focus on 3 areas. One is drag sails, the other one is propulsion, and re-entry satellites. It's the University of Surrey who is building the inflate sail as we speak. I hope it will be completed very soon. That can potentially deorbit satellites in a cheap and efficient way after their use. A similar satellite is built by the University of Aachen. Propulsion satellites come, for example, from Italy, from La Sapienza in Rome, and from Lithuania. And then there are 3 satellites that test re-entry technologies. For example, a French satellite called AMSAT that has no thermal protection, but is just measuring the phenomena related to the early re-entry phase. And then there is the VKI Karma satellite, is shown in the middle of these three illustrations. That is a fully thermally protected re-entry satellite that will take measurements during this re-entry phase and will send it later via the Iridium to us. That's very excited, and in contrast to many other space technologies, there's very, very few data available for this space mission arc being the re-entry. It's only few like the ARD or the IXV that flew 2 years ago, and will be among the very few who can hopefully will be able to say that we took measurements during the re-entry phase. On top of these three satellites, almost all of our QB50 satellites have some kind of new sensor that has not been flown before, and they also contribute to this in-orbit demonstration objective. Can go to the next slide, which shows the status of the space segment, or say a sample of the space segment. You see on the bottom the fully integrated satellites from Finland, from Czech Republic, from Greece. On the top, you see the engineering model of the VKI satellite. You see parts of the thermal protection system. So many satellites are fully integrated now. Some are in the final assembly steps. So that's going very well. My favorite satellite is the one on the bottom right. It's our Swedish satellite, which is shown on the next slide in a bit more detail. That was the satellite that arrived just last Friday at ISS premises. It is a collaboration between a Swedish university, Luleå University of Technology in Kiruna, and Open Cosmos, a company based in London. So it arrived last Friday. We did the necessary checkout activities. We did a refurbishment of the sensors, and we are extremely glad that with this satellite, we start now the CubeSat reception at ISS premises, and as the last step of the launch preparation. So that was, I spoke about the science and the space segment very briefly, but I also said what is most exciting to me is actually the ground segment, and part of the ground segment is the frequency use. And before talking about technical details, you may see on the next slide the two important points of the collaboration between this project, for which I'm the project manager, QB50, and the radio amateur community. First of all, the radio amateur community has helped us a lot in the beginning, in the initiation of the project. Graham was the chairman of a working group, the ground station and frequency working group, and has advised us on how we actually can carry out this project. This support was enabling to us. Some key requirements that were formulated years ago were, for example, that no VHF shall be used for downlink. That wasn't at all obvious in the very beginning. A bandwidth of 20 kilohertz for the UHF downlink. A very pragmatic requirement was formulated by Graham that we here at VKI shall make sure that all CubeSat teams always use UTC time on all network computers, because otherwise we'll never be able to just know when which measurement has been taken. Very practical, very important. We'll take a lot of care to verify that the CubeSat teams are compliant to these requirements, also to the last one. Then in 2013, we have agreed with AMSAT, NL, Netherlands, UK, and France a memorandum of understanding which formalized this support, where we have agreed that in exchange for support to the frequency use of our satellites which have a lot of which purpose is to some extent experimental, to some extent educational, but to a good extent also science. In exchange for the support to the frequency use, we would embark 2 transponders on our test satellites, on our Precursor satellites, which were launched in 2014. So these 2 points of collaboration are extremely appreciated, extremely important to our project, and we appreciate a lot. If we go to the next slide, we see a rough illustration of the frequency that we are currently using, all coordinated between the ground segment engineer here and Graham. We use in total 25 frequencies for uplink, 8 of which are in the VHF, and then on the higher frequency side, we use a number of UHF frequencies for uplink too. If we have to share frequencies, then we do that for uplink with we share the same frequencies in different locations of the Earth. For example, North and South Europe use sometimes the same uplink frequencies. Or sometimes we use the same uplink frequency, obviously, if a ground station has to serve 2 satellites, that can also work. For downlink, we don't have VHF, but only UHF frequencies, in total 42 unique frequencies. And to some extent, we also share here frequencies at different locations. The frequencies are a bit sorted. Graham advised us here according to modulation and spectral efficiency. So we'll use, when we'll launch, and we'll scheduled for launch 30th of December, we'll use quite a bit of this radio amateur frequency spectrum. Next slide. So this frequency use is part of the ground segment, which consists of roughly 50 radio amateur ground stations. It's quite a big network, even though their interaction is not so. It's not Genso type. It's not a network, but more a collaboration, a re-collaboration between the different teams. But there exists also some central functions. So we have at the VKI what we call the Display Processing and Archiving Center, which is somewhat similar to the FunCube data warehouse. Here we will store, in particular, the science data, also the health information, the work data. It will be displayed. You will see that on the next slide. That will help us here at the VKI to support all the CubeSat teams, telling them if we think their satellite may be in bad shape or not. The part of the ground segment, as mentioned, is the frequency coordination with you, and also to some extent the radio amateur coordination, who can participate in QB50 when they, for example, receive a signal. They can upload that to our DPAC. That's shown on the next slide. And we go one step further so that we see the coverage. You see there's a bit of lag here, so I'm sometimes not sure if you see the same as I see. You see the world map with the approximate location of all our ground stations, or the amateur ground stations. It's not absolutely accurate. For example, the team in Singapore has left, and what gives a good impression, and it gives also quite a good impression what our access from our ground station network is to low Earth orbit. And it's a pretty impressive figure, I would say, because we have access to maybe a quarter up to a third of, we have access to space over a quarter of the Earth landmass. It's pretty impressive. Next slide. So we have this data warehouse, which we call the DPAC. We'll use it to display the position of our 50 satellites. And it will also be enabled to upload data. that's already shown on the next slide, will be rather simple. If you have received a beacon data, you can just upload it via a web form. If you are a member of QB50 and you use the satellite control software developed by EPFL in Switzerland for QB50, then the upload of your data should be quite automatic. Go to the next slide. Quite important, and we had an enormous amount of trouble with that, is with the launch segment. We went literally through a roller coaster, starting with a Russian rocket called Stiel. Then we were promised a launch on a Ukrainian, Brazilian rocket called Cyclone 4. Also, this didn't work out because of geopolitics. In the end, the International Space Station is our choice. The US company Nanox made us a very good offer to launch the majority of our satellites from the International Space Station via the JAXA robotic arm. So 40 satellites will be in a 50-degree orbit around 400-kilometer altitude. And we expect that the launch will take place with the Antares rocket 30th of December. We'll then do two deployments. First one after roughly a month, the second deployment after roughly 3 or 4 months. And these are our requests to NASA, but only NASA will tell us in the end when they will actually deploy us. Since I've seen quite some presentations with the concerning work with the ISS, you certainly also know that our research is not the priority here, but is always astronaut safety, astronaut time. So they will try to deploy us in this, after these requested months, but it might be slightly different. But because the ISS does not fly over the poles, and the poles are scientifically very interesting, we reserved a bit of launch budget to launch in total 8 Cubesats in a polar campaign. Again, we had trouble. We were to launch on a Dnepr rocket that appeared to be a very stable launch service. It turned out not to be. We haven't signed any launch contract with another company, but the illustration on the very right-hand side shows the likely new launcher based in India. So yeah, we're quite close to the launch, particularly for the ISS, and that makes us very excited and very happy. Sometimes also a little stressed. If you go to the next slide, I think there might be a mix-up. We should go to Launch Campaign 1. It shows the activities that needs to be carried out before the launch. Is the obvious thing. At the moment, we are the last steps of assembling the satellites. Then these satellites will go to ISIS for a checkout. So the teams should come there, check if the satellite's working after the transport. We'll do a sensor refurbishment. For example, the feedback sensor need should be Launch Campaign 1. If you go one more further, I see these slides changing. If you go through it, there is Launch Campaign 1 and Launch Campaign 2, and Launch Campaign 1 comes after Launch Campaign 2. The stream is a bit behind, so I sometimes don't know exactly where you are. Yet it's not so important. It's the obvious, and certainly I can pass that message also verbally.
It should be okay now.
Yeah. The last steps now are done at the Cubesat premises in the laboratories of the teams. For example, also at VKI, but also in laboratories in China, in the United States, in Austria. Then they come to ISIS, we'll do a last check there, we'll do a flight readiness review for the first for the satellite, then for the entire system. And then NanoRacks will come to ISIS premises in the Netherlands, put our satellites into their deployers, and take them with them to Houston. From there on, we will not have access to it. They will hand it over to Lockheed somewhat in September. And then they will go to the launch site, the Mid-Atlantic Regional Spaceport Wallops, and hopefully we will launch 30th of December. Looks pretty good. It also means that our satellite teams have to work hard now to really finalize their satellites, and those who have been involved with satellites, they know that there's always some trouble in the last minutes. If we go one slide backwards, we go to the slide Launch Campaign 2. Here we have a list of activities that come after the launch. We'll do the commissioning. First, we'll do a commissioning of the platform as such, communication systems, for example. Then we'll do the attitude commissioning. All the CubeSat teams should achieve this 3-axis stabilization. If they have done that, we'll test our sensor units. And then there might be a bit of a waiting period for the different, until a good majority of the satellites are then ready to carry out the science campaign. There will be, of course, enough time for each CubeSat team to do their own science if they have a separate instrument on board. Some have special magnetometers or cameras. They will have time in between to use that too. But at a certain moment, we want to carry out the science campaign. So where we really do these multi-point measurements, all the CubeSat measure at the same time in situ the composition of the thermosphere. And that will be very, very exciting. Then there will be a free phase, how we call it, the gray bar there, where we leave the teams to what they do, and we want the CubeSat teams to decay in altitude, and hopefully then later we'll start again when the satellites are at the lower end of the thermosphere. This is very unexplored territory, and hopefully we'll do a second science campaign at that time. So we go 2 slides further. That there's a slide called also launch segment that illustrates a bit the decay of the satellites and how that relates to the science, while this slide is not fully up to date. The important message here is that having, say, 2 campaigns, and the ISS campaign has 2 deployments, the satellites will be at different altitudes. And that will allow us not only to do a multi-point measurement, say, in terms of longitude and latitude, but also in altitude. And that's scientifically very interesting to have this wealth of data, longitude, latitude, and altitude. Unprecedented and hopefully appreciated by the scientists. Next slide. We talked about it already, the Precursor campaign, and the picture on the bottom right, you have seen it already today. And these are our P1 and P2. And we brought these satellites to space just to test deployment system, the sensor unit, the attitude control system. And it turned out to be a very, very, very good idea. While we have achieved basic scientific measurements, we have really learned a lot about flaws in the documentation. We have learned about flaws in algorithms of the attitude control system, flaws in assumptions, for example, on tumbling rates. The satellites were tumbling much stronger than we had hoped for, but we were able to overcome it and find solutions well ahead of our main science campaign. So that was an excellent idea, and And yeah, these satellites are still in orbit. We heard of they are still in use for the two transponders that were embarked, the two AMSAT transporters. Next slide. That shows a picture of the launch. Took place in 19th of June 2014. So that's now more than 2 years ago. And one satellite still working very well, P1, while the second one had the damage in the past of one subsystem and unfortunately is not functional anymore. Next slide. With the heading Precursor Derisking Campaign. And something. Precursor Derisking Campaign. So we took our first measurements. P2 is unfortunately defective. We learned a lot. That was the overall purpose of it, and that will feed that lessons learned into the campaign, into the main launch campaign. Transponder of P1 is in use, as we have learned today. Another achievement was that these two satellites were for the first time given the European Oscar names. That was quite an honor for us, and yeah, showed the collaborative objectives of this QB50 project. Next slide. That was the technical side, the scientific side of QB50, and we're also organizing the European Cubesats Symposium, which I need to advertise here a bit. We had, you see it on the right-hand side, workshops at the Von Institute in Belgium, in Switzerland, in China, that's on the bottom, last year in Liège. This year, our European Cubesat Symposium will take place in London, 7th till 9th of September, Imperial College of London. And I want to invite everybody to join, all those who are interested in CubeSats. Next slide, please. I'll conclude that part of the presentation for QB50 with the acknowledgements. I started with it. The VKI is here the coordinator. We have a consortium out of 15 partners from China to the United States. So we have a Chinese university, we have Stanford University, we have two in the UK, UCL and Surrey University. We have sensor unit suppliers in Norway and in Germany, launch providers in the United States and likely in India. We have our CubeSat community from all over the world. We have a very strong support, which is one of the bases, one of the pillars of this project is the radio amateur community. We receive support from governmental bodies, Belgian Space Agency, the International Telecom Union also have supported us way beyond what they should have done. So did the to ESA. So did ESA. I think my time is running out, but I'm done now with the acknowledgements. On the next slide, you see where I am sitting at the moment. That's the QB50 team with all the team members, which I also owe some appreciation here because they're doing an extremely good job in supporting all the CubeSat teams in the entire world to get their satellite ready. And that concludes the this part on QB50. I have one more slide on one upcoming project. If we go to the next slide. It's an introductory slide, webcam, W-band CubeSat for atmospheric measurements. That's a project that we proposed to the European Space Agency. Next slide is only one to shortly introduce the concept. What we want to do is we want to build a 3-unit CubeSat that sends a 76 gigahertz beacon while orbiting from low Earth orbit in order to allow a measurement of the attenuation of the atmosphere. For that, it would be of advantage not to have an SS orbit, but be able to sample different LTANs. It should also send a reference beacon at 47 gigahertz, because then because we could take at the same time measurement at 47 gigahertz from a geosatellite. That relates to the purpose of this project is because maybe in the future 76 gigahertz frequency could be used for geo applications. So the Space Agency thought of maybe using a CubeSat technology to carry out this attenuation measurement. That would be unique because most of the ITU models are, even in Ka-band, only done based on measurements from geo. Using a LEO satellite will enable a much more accurate modeling. Therefore, we want to use the LEO satellite. We want to have a reference beacon 47 that we could compare to a measurement at 47 gigahertz from geo. Project duration should be 2 years, maybe with an extension of 2 years, and it was right from the beginning to be carried out in collaboration with the AMSAT community. Community could take secondary measurements, maybe not of scientific rate, but of a practical quality. And we also wanted to put a transponder payload. When I applied to come to the colloquium, that project was proposed to the Space Agency. Unfortunately, at the moment, it is on hold. We're putting any effort necessary to have it in the end being active, to have it accepted by the European Space Agency. And then, if that should be the case, we'll be very glad if the radio amateur community could be involved, could collaborate, if we could collaborate with you on this project. So that's my last slide then. I thank you very much for your interest. Thank you very much for having me presenting